We've been talking a lot about electrification today. We're talking obviously a lot about hydronics, how the two come together. And I wanted to put together a presentation that shows you a real project that was done within the last year. This is actually a parsonage at the church I attend in upstate New York. And I'll give you kind of the background story as we go through the slides, but the short version is we took a 45-year-old double-wide mobile home, took it off its foundation, rebuilt a structure, stick frame structure over that, and that is heated with an air-to-water heat pump. It is doing panel radiators. I mentioned this morning we had a project with panel radiators operating at about 90-degree water temperature. And I'll show you the schematic, and we can, you'll see how basically we've pulled together space heating, cooling, domestic water heating, and heat recovery ventilation, pulled it all together in one system. The transformation of a building and its HVAC system. Over there on the left, that's the 45-year-old double-wide mobile home. In the United States, mobile homes are built to what are called HUD standards. These structures don't necessarily meet New York State building code. And being 45 years old, you can imagine the insulation systems and so forth were pretty marginal in this building. And the new structure, I would call it state-of-the-art. So it was a pretty big transformation. Over the years, what had happened with this structure, as you can imagine, at a church, you have a lot of volunteers that are very willing to get in there and do things when, something's leaking or, a window won't close or whatever it is. We got a lot of willing people, but the skill level varies, and that's putting it kindly. So over the years, this structure had a lot of different attention and various attentions to detail. And basically what happened is it got to the point where there was mold forming in the structure, the roofs were leaking, the kitchen cabinets, the doors were bad shape. And, it's like an old car. At some point, you're kind of throwing good money after bad. So the church made a decision to take it down. Now, the good news is that the foundation was in really good shape. This was in very well-drained sandy soil. It was a block foundation, and it looked like it was built yesterday. So we didn't want to take it down through the foundation. We took it down to the foundation. I'll show you some slides. This is basically the elevation views of the structure. It's nothing architecturally elaborate, but it's very functional, and it was designed to be, a quick build. It was designed to be energy efficient. It was designed to have low maintenance, and hopefully you'll see how it was accomplished here. So the first part was demolition. And anybody here ever taken apart a mobile home? They're kind of interesting projects. There's a lot of glue and staples involved. And we had hoped that we could salvage some of the lumber because we were building this, when the lumber prices went crazy. A 2x4 8-footer in our area, when part of this project was being planned, it got up to $12 US for one stud. And OSB, 7/16 OSB, oriented strand board, that got up around $54. So we wanted to see, can we salvage lumber out of it? We did salvage a little bit, but a lot of it went into the dumpster. And you can see here, we're basically down to the foundation. And we had to be pretty careful tearing that apart. So, block foundations like that, you can damage them pretty easily, especially with an excavator tearing down the structure up above. We did plan a couple foundation additions. You can see right here, we used a system called shallow frost-protected foundations, where the footing is actually only down about 2 feet below finished grade, and then there is rigid polystyrene insulation put around the top of the footing. And what that does is it prevents frost from penetrating below the footing. So it allows you to get a stable footing, but not have to necessarily go 4 or 5 feet deep. Again, we added a couple small areas here in the upper middle there. You can see we added a vestibule. It's a small area. It's only 8 by 12 feet, but we decided to do floor heating in there. So we tied in two small areas of slab-type radiant floor heating with 10 panel radiators. And we designed the system so it all operates at one water temperature. We don't have to have mixing involved. We used a system of framing called 24-inch inline framing. again, I know this is mechanical contractors. It's a pretty simple idea. All your framing lines up. The studs, the floor joists, and the roof trusses all are in the same plane, and that plane is repeated every 24 inches. That's a very strong structure. It's also a structure that builds quite a bit faster than traditional 16-inch on-center framing. And you can see some of that in the lower left there. The project actually got underway a little less than a year ago in October, and a crew of 4 were able to have the thing completely framed up in about a week. The roof deck was on 1 week after they started framing. So this went pretty fast. And again, a lot of that is just due relatively simple plan and the 24-inch on-center framing system. We got it weathered in November, by mid-November, and in upstate New York, by mid-November, you can get some snow off Lake Ontario. You folks are very kind. You send that cold air down over our lake, or the lake we share, and we reap the benefits of that. So we can get a lot of lake effect snow. You probably know, anybody here ever heard of Buffalo, New York? Yeah, like last year they got 4 or 5 feet. I think they were planning a football game, the Buffalo Bills, and they had like 5 feet of snow on the football field. And of course they canceled the game. So anyway, we want to get this thing buttoned up before we get into some really bad weather. 24-inch overhangs all around. You can see the heat pump in the upper right corner there. My laser is not really working here, but in the upper right corner, if you look on the right side of the house, you'll see the heat pump. It's very similar to the heat pump that's over here. It's up on a stand. I'll show you. You can see the stand there in the lower left. It's a pressure-treated stand. It was designed to keep the unit up above the snow. You don't want to set these heat pumps on the ground or 2 or 3 or 4 inches above the ground for a couple reasons. One is snow. Secondly, what will happen is when these units defrost, the frost will build up on that outdoor coil, and when they defrost, they can drop a quart or 2 of water, and if that water goes down and just sits on the ground or sits on a pad, it will start to form like an ice bathtub under the heat pump. And pretty soon that water will actually start to go up into the cabinet of the heat pump, and I do know of a case where the coil actually was ruptured. The outdoor coil, refrigerant coil, was ruptured due to ice expansion. So get the units up above the snow, above the ground, above the insects, the grass, the leaves, and so forth. And I would suggest at least a foot, and if you're in a deep snow area, maybe even a couple feet. This unit is up at least a couple feet above finished grade here. Floor plan, again, it was quite a bit of space here. It was a big open area in here, kitchen, dining area, living room, a couple bedrooms here, master bedrooms back here. And keep in mind, we had to design this around an existing foundation. It's not like we could make major changes in the foundation. So, and right now it's actually 5 bedrooms, 3 full bathrooms, and design load on it's about 35 or 36,000 BTUs per hour, and that's at -5 Fahrenheit outside. Now we use panel radiators, and those orange rectangles are where we put the panel radiators. We size these panel radiators up around an average water temperature of 110 degrees. We actually found that we can run them quite a bit lower than that and still get the output that we need, but we sized them up around an average water temperature, 110. And again, where'd that come from? This morning I mentioned my own criteria. I try to encourage anybody designing modern systems today, keep the water temperature at design load no higher than 120, lower if possible. Okay, so you're well within the realm of how heat pumps, as well as modulating condensing boilers, or if you want to add solar thermal, all those heat sources are going to operate better at these lower water temperatures. Now, if you look up at the top up here, we used attic trusses. And attic trusses allow you to create a partial livable space within the truss itself, as opposed to a truss that's just full of webbing and really doesn't, provide any extra space. So 2 of the bedrooms and 1 of the bathrooms are actually in the 2nd floor up where you see the silhouette up here. That's 16 feet wide. It's got a full nominal 8-foot ceiling on it. It does have some sloping sidewalls. You can actually see it over here. And the entire structure is insulated with spray foam. There's 7 inches of 2-pound per cubic foot density spray polyurethane foam, and that actually goes right up the underside of the roof sheathing, and it comes down, it covers the area here over the top plate, so you get a nice continuous, or almost continuous, it isn't continuous at the framing, but you get a nice insulation system, and by insulating on the underside of the roof sheathing, your mechanical systems, ducting, is all being run through the trusses. It's all within the thermal envelope of the building, as opposed to insulating on the flat ceiling and then having ducting that's in unconditioned space. Okay? There's a floor plan of the second floor. There's pretty large bedrooms. Basically, these are about the same size. We did put a couple closets in there that aren't shown. There's a bathroom here. And then the air handler. The air handler is for cooling. It's a chill water coil in an air handler. That was actually parked behind the bathroom, and there's an access panel to get in there. And then the U-shaped stairs here to go downstairs. Okay? And there's a couple panel rads up there. So here's some of the stats on it. The design heating load worked out about 13.5 BTUs per square foot per hour, which, you know, again, that 10 to 15 BTU per square foot per hour range is very achievable today. I know we were talking, I think Gary talked about a project was even less than that, maybe 6 BTUs per square foot per hour. Again, everything was spray foam. The walls, the underside of the roof deck, and we actually extended the spray foam. You can actually see it lower left here. We wanted to make sure those band joist areas were well sealed. Band joist areas are a high percentage of total air leakage in most buildings because the foundation isn't perfectly flat. The wood shrinks and you get gaps between the sill and the foundation. And even though there are sill sealing gaskets that are put in there, it's still an area prone to air leakage. So we spray foamed it, and the spray foam actually comes down, comes out over the sill, and ends on the top of the block. So that whole area was sealed up. And actually here you can see a couple of the half-inch tubes. These just go up to a panel rad. So there's just 2 holes, 3/4-inch size holes, 2 inches on center. The 2 pieces of tubing go up. They go into a dual isolation valve. There's a ball valve here and a ball valve here. If you ever have to take that panel off or isolate it, you just take a screwdriver, close those 2 ball valves off, and there's unions, half unions here, and you can break those unions and you could lift the panel right off. Here's the spray foam again, 7 inches, which is R49 up here. The walls were either 3.5 or 4 inches. And actually the people that did the spray foam had excellent control on that thickness. I went around several places with rulers, double checking, and they were spot on with their thicknesses. So really good R values, not passive house R values, but very good contemporary R values that would easily meet the codes up there. The other thing about spray foam, incredible stiffening of the structure. If you've ever been in a house, before you put the sheathing on, you can actually grab the studs. You can shake the whole house. The sheathing, of course, will stiffen it up, but once you put spray foam in there, you've all seen The Wizard of Oz, right? Remember Dorothy's house lifts off with the tornado? And I was telling the builder, if this house is ever picked up by a tornado, it's going up in one piece. It's really that stiff. It's incredible. And acoustically, it quiets the house down, too. Noticeable difference with any cars going by on the road. It makes quite a difference acoustically. The windows were double glass, obviously, low E, argon-filled glass, and they're about R3.5. Now, our basement, our New York State code requires a basement to either be, the walls have to be insulated, or the space has to be treated as unconditioned space, in which case you have to insulate the underside of the floor deck, and you have to insulate any piping or ducting that's carrying heated water or warm air. So we did end up insulating the underside of the floor deck. That was actually done with mineral wool, 6-inch thick mineral wool. A lot nicer to work with than fiberglass. How many here love working with fiberglass insulation, especially over your head? That's a bad day, okay? Okay, so that's the structure. Let's talk about the mechanical system. Now, I showed you this slide this morning. I didn't really get into it, but I'll start over here. It's a nominal 4-ton, low ambient air-to-water heat pump. It's a monoblock. It came pre-charged with refrigerant. It's actually rated to operate as low as minus 22 Fahrenheit. Now, granted, the capacity in the COP is not really good at that point. I'd have to look up the COP, but I'm guessing maybe 1.2, something like that. It's still better than electric resistance heat. And the capacity is probably a third or less of what its nominal capacity is at those extreme temperatures. But you aren't at those extreme temperatures very often. In this location, it might hit minus 22 for an hour, maybe in an average winter, something like that. So the machines can operate at low ambient. Now, I'm going to kind of follow the water here. We come in, and there's a motorized diverter valve here. This is 1-inch piping, copper piping. And the diverter valve can either direct the water up into this tank, or it can direct it when it's in the cooling mode, it can direct it down through insulated 1-inch PEX to the coil in the air handler. So it's just a fork in the road, depending on whether you're in heating or cooling. The buffer tank is actually, it's a TurboMax tank, like the tank that's over here now, and it does two things for us. It provides buffering, because we have a lot of independently controlled panel radiators up here. All these panel radiators have thermostatic radiator valves. So there's literally 10 different zones, if you will, 10 different points where you can adjust this, plus the 2 areas of radiant floor heating. You can see those tagged on over here on the left side. Now, again, these are all non-electric thermostatic radiator valves. You might be wondering, well, how'd you control the radiant floor circuits? Well, we use non-electric thermostatic radiator valves. You can buy these valves so that the valve has a what do I want to call it? A device that screws on the top of the valve like a TRV, but it goes to a capillary tube, not a capillary tube, a capillary tube, and the capillary tube goes up the wall, and there's a wall-mounted control for it. So you can adjust, the 1 to 5 range, just like you would on a standard knob that would be on the panel rad. So there's actually 12 different zones, all controlled by thermostatic radiator valves in the system. And there's one little pump here. This is a Taco 0018E. It peaks out at 44 watts. It's running on proportional differential pressure control, and that pumps the entire house. And it has a Bluetooth output. You can get an app on your phone. We watch this pump operate. Typically, it's between 20 and 30 watts. So you're delivering all the heat you need to this house using 20 to 30 watts of electrical input. And again, remember, we talked this morning about distribution efficiency. You could probably pull your phone out and do the numbers, 35,000 divided by, say, 25 watts. It's pretty good on distribution efficiency. Now, that tank, the TurboMax tank, has those internal, you can see them over here, the copper coils. We feed our cold domestic water into those coils, and we're using that for preheating. We can bring that water up to about 100 degrees with this tank. Now, we could set the heat pump to bring it up to a higher temperature, but the existing building had a 2-year-old heat pump water heater that was working great. So we decided we will use that as the final temperature boost, and that way we could keep the water temperature in the buffer tank as low as we could and still satisfy the heating load. Now, we could have used outdoor reset control on here. Quite honestly, we looked at the difference, and there really wasn't much difference in performance. So it's a simple 2-stage controller, set point controller. First stage controls the heat pump. Second stage controls an electric boiler right here. This is an Electro Industries boiler, 9 kW. I'll show you a picture of it. Just mounts on the wall. And if that's needed, it kicks in on the second stage. So I believe right now, I'd have to check the current settings, but let's say we had it set for first stage at 100 degrees. If it drops another 5 degrees, because the heat pump isn't keeping up, we'll bring on the electric boiler. We actually used the electric boiler for about a month just to provide heat during construction before we had the heat pump connected, and it worked fine. So again, the domestic water comes in here, goes up through the copper coils. It gets, I'm going to say, 80 to 90% of its temperature lift right from the water in the shell of the Turbomax tank, and then it goes into the heat pump water heater. And finally, we decided, because of where the plumbing fixtures were, they were spread out quite a bit, to put a recirculation system in there. So there's a little small stainless steel circulator. All that piping is insulated, and that provides more or less instant hot water at the faucet. A little hard to see it here, but here's the heat recovery ventilator down here. I think, if I remember right, this was either April Air or Renew Air, or one of those. Obviously, there's many of them on the market right now. And the outdoor air comes in, it goes through the core of the HRV, and it's injected into the return header of the air handler. Now, we found something pretty unique with this air handler. We could operate that air handler for cooling. We could operate it at, say, 1,100 or 1,200 CFM. You know, we got 3 tons of cooling, nominal 400 CFM per ton. You can go a little less than that, maybe 350 CFM per ton. Now, we could have kept that air handler running 24/7 and just use that to push the air around the building, but we really didn't need that kind of airflow rate when we're just moving ventilation air. So we talked to the manufacturer, and they said, well, we can actually program the ECM motor and give you a speed tap so that you can run this thing at about 150 CFM during ventilation mode, and when you go into cooling mode, you can kick it up to 1,200 CFM. So that's the way we set it up. So the HRV is doing roughly about 120 CFM. It injects it into the return side of the air handler, and then nominal 150 CFM, 24/7, moves it through the building. We actually set it up too, so in the bathrooms, there's timers, and if you press the timer, it'll kick the HRV into a high-speed mode, so it helps to move moisture out of the bathrooms. We've got a glycol feeding system over here. This all has a 30% propylene glycol. It's actually got Canadian glycol, Chemfax glycol in there. And the header system that you see up here, very simple. Now, one of the things we could have done here, and we thought about it, we could have home-runned all that PEX tubing back to a manifold, you know, a typical radiant floor manifold. I'll call it a compact manifold. That would have required a lot of tubing to bring basically 2 floor heating circuits and 10 panel radiators all back to one manifold station. A lot of tubing and a lot of time with a drilling holes through floor joists. So rather than do that, we had this girder that went right down the center line of the house, the full length of the house. It's 12-inch deep laminated veneer lumber girder. We got, and you'll see it in just a minute here, basically we just hit the middle of that girder with 1-inch piping coming from the buffer tank here. This is 1-inch piping, and then we split it to both directions with 3/4-inch pipe, and then we just put T's in. You can see each one of these is a press-fitting T, 3/4 by 3/4 by half, and then an adapter over to, it's actually 1/2-inch PEX, aluminum PEX tubing, and then those run out to the panel reds. So we call this an extended manifold. It's still putting all these heat emitters in parallel. It just doesn't bring all the tubing back to one close location. Either one of those systems, whether you brought it back to a compact manifold location or you spread it out, they're both going to work for you. It's just a matter of how much tubing you want to use, how many holes you have to drill, and pulling all that tubing through the floor joist. So here's some photos of it, just kind of looking at the equipment. There's the heat pump up on a stand. These are flexible hoses with a stainless steel braiding on the outside. They're all insulated now, and it doesn't show it here. They're going to be wrapped with an ultraviolet resistive tape too, so that insulation doesn't degrade over time with sunlight. There's the electric boiler, very small, It's like 16 inches tall, maybe 6 inches wide, 9 kW. Here's the turbo max buffer tank. This is the valve. This is a Coquitlam 1-inch motorized 3-way ball valve. And it's got a 24-volt actuator. Power goes to one lead, turns it all the way to one direction. You power another lead, it goes all the way in the other direction. And I'd have to look it up, but I think it's 30 seconds, 60 seconds, something like that. It's not an instant move, so it powers over. There are limit switches inside, so if you're designing controls, you could design it so when a limit switch tells you the valve is in one position, you allow some other device, be it a pump or heat source, to operate. And the expansion tank and the glycol feeder, okay? Again, this is all off-the-shelf equipment. Let's see, here's a panel rad. These were by Meissen. This is about a 5-foot by 2-foot panel rad. It's about 4 inches thick. There's the thermostatic radiator valve on there. And one of the nice things about those radiators, the Meissen ones, the piping connections all come up through they're all centered on the radiator. So if you're roughing in the piping, you don't have to know, other than here's where the center line of the radiator is. You just go 1 inch either side of center line, bore your holes, and you're all set. Other ones are fine. You just have to know where those piping connections are. They tend to be over to the right side, closer to the integral valve in the radiator. And there's a 0018. Again, that's pumping this entire distribution system. And this pump will vary its speed as these thermostatic radiator valves open and close. So as valves start to close, the pump will sense an attempt to go to higher differential pressure, and then the electronics in the pump will reduce the speed of the motor and bring the differential pressure back down again. So I call it cruise control for differential pressure. And again, that's a built-in algorithm, and pretty much all the pumps, major suppliers in North America, they all have these products now. Okay, cooling mode. I mentioned here's the valve. Flow comes, this would be chilled fluid now coming in from the heat pump. It hits that valve. This is 1-inch PEX with 1/2-inch elastomeric foam insulation, all glued together, taped up. You've got to do the insulation right with chilled water. If you don't, if air can get to your chilled water piping, I guarantee you're going to have condensation, and it's going to drip somewheres. Maybe it's on the basement floor, maybe it's above a drywall ceiling, and it's going to get your attention as a callback very quickly. So chilled water cooling is very viable today in residential, but be careful with the insulation. You want to do if air gets to the pipe, gets to anything with chilled water in it, it's going to cause corrosion. Okay. You can see some of the insulation here wasn't finished yet. That's what the air handler looks like. It's from a company down in the States called B&D Manufacturing. They're big in the geothermal market. They make the pumping stations. But nice big coil. That unit is basically a 2-foot cube. It's 2 foot high, 2 foot wide, 2 foot deep. And there's an ECM blower in there. And as I mentioned, the manufacturer actually, they did a little custom programming for us so we could run that at 150 CFM or 1200 CFM, just 2 different wire tappings. Okay. It's copper piping supported on channel strut. One of the things that I guess I'll throw this out as an encouragement to the circulator manufacturers. One of the things I'd love to see in our market, I think we really need it, is good insulation shells for the volutes on circulators. Because as we go towards heat pumps, whether they're geothermal applications or air to water, we're pumping fluids that are well below dew point, both in geo applications in the winter and chilled fluid for cooling in the summer. And I can tell you from experience, an uninsulated pump volute will look like they all turn orange within about a year, and it's not paint, it's oxidation. It doesn't stop the pump, but you're going to see a lot of oxidation. The other thing I'm going to throw out as encouragement to manufacturers, insulated isolation flange systems. okay, where we've got the flange and the ball valve, several manufacturers have those. That zinc plating will not hold up long-term with chilled water. It will corrode. So we need, what would be ideal is to go from the insulation on the pipe right through an insulated isolation flange, and then right through the volute, the insulation shell on the volute of the pump, and make that all continuous. I think that's a great opportunity, not only for the circulator manufacturers, but other parties that might want to develop that. That's something this industry needs. There are a few commercial-sized pumps that do have insulation shells, but we need that on some of these smaller circulators. Domestic water, there's a little Aquatherm stainless steel pump here that just pumps a recirculating system, okay, up here. Nothing really exotic about that. But we wanted to tie recirculation in because of how the fixtures are spread out in the building. Heat recovery. So there's what the unit looks like. There's a lot of them you can choose from. I think these things really originated up here in Canada, right? Van E was one of the originals. Again, it just ties into the return side of the air handler. And we put a filter grill in the ceiling of the hallway. All the return air from the entire house goes to that, which raises a question. What happens if the doors are closed on the rooms? You're putting supply air into the room. If the door is closed and it completely blocks the opening, you're not going to have proper airflow. So we found a company. It's actually up in New Hampshire. It's called Tamarack Technologies. Anybody ever heard of them? Tamarack Technologies. They make these grills that can be cut into the bottom of a door, and they are designed to suppress acoustic transfer as well as line of sight transfer, light transfer. They have baffles in there, but they allow air to come through, and you get a pretty significant return airflow. In fact, Allison Bales did some testing on these things with manometers, and he was demonstrating they work pretty well. The thing I liked about this, we didn't have to do return air ducting to every room. We just let it all come out into the central hallway, and then it all goes up through a filter grill. And instead of just cutting a hole in the wall that obviously light and sound would come through, we put them on the bottom of the doors. You just take a saber saw out an area, and they slip right up onto the door, and a couple screws at the bottom hold them in place. So that's how the return air was handled. Let's see, I think I've covered most of that. Now, we put a 100 amp sub panel from the main panel. The main panel in this building was a 200 amp panel. We put a 100 amp sub so we could keep all the wiring for the mechanical system on that one sub panel. And then down here, it's a little hard to see it, the control system. And again, I'll make the slides available as PDFs. It looks complicated, but really it's a bunch of switches. There's basically one switch that sets the mode of the system. It's either heat, off, or cool. It's just a toggle switch with a center off position, okay? And then that switch basically interacts with other devices, a couple relays, triple pole, double throw relays, industrial relays. Again, you can buy them very easily. And we created the logic to operate this system using what I call hardwired logic. Now, obviously there's other ways to do it, programmable controls and so forth, but it's relatively simple. It's really not a very complicated thing. When you put the switch to heating, it turns on that little 0018 circulator, and it runs 24/7. And if you calculate how much, let's say it runs at 30 watts for 24 hours, our rate for electricity was about 16 cents a kilowatt hour. It's like 12 or 15 cents a day to operate the circulator. You don't need to turn it off. And that way, the TRVs are always able to fine-tune the temperature in each room. There's always flow during the heating mode operation. When you turn the switch to off, it just turns that pump off. So pretty simple. Here's one of the TRVs. Here's the two mode switches. They're labeled now. And next to it, you see this is a cooling thermostat. It's pretty hard to find a cooling-only single-stage thermostat. Anybody know of one up here? Single-stage cooling only? most of them are set up for heat and cool. And what I did is I actually took the thing apart and soldered a couple wires in it, so we disabled any heating function. And I've got to go back up and actually paint over where it says heat, because I know what's going to happen. Somebody's going to say, I want heat, and they're used to just pushing the switch on the thermostat, and that doesn't do anything. So I want to wipe that right off the thermostat. But it works. It's really pretty simple. That's just a little bimetal thermostat. It's like a $15 thermostat. The rest of the wiring, I mean, you've got a separate double pole. I think it's a 50 amp breaker on the heat pump. The electric boiler is double pole. I think that's a 60 amp breaker. The air handler is a 15 amp double pole. That's set up for 240 volts. And then there's like one line voltage circuit, 120 volt circuit that does the circulators. And there's a couple controls over on the side here, okay? One of the controls we built in here, and this is something to think about, let's say you've got a heat pump, air to water, and it's doing cooling, okay? And in the summertime, you want to switch the heat pump from cooling over to heat that buffer tank because you want to maintain domestic hot water. You can't do them both at the same time. One of those modes has to be a priority. In this project, we made cooling the priority. So if we switch from cooling and go immediately to heating, what's going to happen is the chilled fluid that's in the piping between the heat pump and the mechanical space is going to get injected into that buffer tank. Now, you may never detect that, but in the opposite direction, let's say you've been heating the buffer tank, it's a hot day in July, you've temporarily shut off the blower in the air handler, and now you come back out of heating, you go into cooling, you're going to send 110, 120 degree fluid through the coil in the air handler. Now granted, that's only going to last 2 or 3 minutes, but the last thing that an occupant wants to feel on a hot day when the cooling system's going is a burst of warm air coming out of the registers. So we set up a control that simply prevents the blower in the air handler from operating until I think it's set for about 60 degrees now. So once that fluid gets down to 60 degrees, which happens quick, when you switch that heat pump over to cooling, it chills that fluid down. It's maybe 5 gallons of fluid with a 4-ton cooling system. It doesn't take long to bring that down. Once it hits 60 degrees, the blower is enabled, and that way we don't get that temporary burst of warm air coming out of the registers. Lessons learned. I made a mistake. I didn't see it coming. Here's where the expansion tank is, okay? Over here, here's that 3-way valve. Now, in the cooling mode, if we look at this line here and this line here, that line is blocked. In other words, there's no way this fluid can communicate with that expansion tank through the red line. And there's actually a check valve. It's a little hard to see it. There's a check valve right there. The check valve was put in so that the cool fluid coming back from the air handler didn't cause any kind of migration into the Turbomax. We want to keep warm water in the Turbomax, chilled fluid in the cooling system. So the check valve was there so we didn't get heat migration. Well, that seals off this path right here. Anybody see what's coming? And I never saw this before. When the cooling system was running fine, when it shut off and the fluid just started to warm up, just ambient energy going into the fluid, just bringing it back up, the relief valve started to dribble. The relief valve is here. And what happened? Well, we sealed off all communication, so to speak, was broken with the expansion tank. And just that chilled fluid warming from maybe 45 degrees up to maybe 70 degrees, that was enough expansion to cause the relief valve. It didn't burst open and shoot a geyser of fluid out, but it would just start dripping. And so it's one of these duh moments, right? Water's an incompressible fluid, and so is 30% antifreeze in water. So we're standing around thinking, oh boy, now we got to open this piping, drain the antifreeze out, and Fortunately, we found a Band-Aid, and I'm going to call it a Band-Aid because I should have caught this earlier. Right here, there is a dual port purging valve. That's 2 hose bibs, one on either side of a ball valve. So what we did is we bought a high-quality washing machine hose and I think it was an Amtrol 15 tank, and we put another expansion tank in, and it solved the problem. What I should have done is put the expansion tank in the design over here. That would have taken care of it. So I guess when you get old and aged in this industry, you do start slipping up once in a while, right? Another lesson learned. I thought all these TRVs were kind of universal, that you could take anybody's TRV and screw it onto anybody's radiator valve. Not the case. The Meissen radiators use a Danfoss valve core, and that valve core sticks out. And here's what happened. We took one, and the TRVs were by Caleffi. So I took one of the Caleffi TRVs and went to screw it on the radiator, and that's as far as I got, right there. Unfortunately, the folks in Italy at Caleffi came up, they had a little adapter, and all it does, here it is, it just, you put it over the valve, it's got a little set screw that holds it in place. It just extends the threads that hold the TRV, and then the TRV threads right onto that. So check if you're working with thermostatic radiator valves, yeah, I guess the default advice, buy the valves and the radiators from the same supplier because they're going to be compatible. If you're shopping around and using different products, make sure you've got compatibility between the TRVs and the valve cores. So those are a couple lessons learned in there. We were able to resolve both of the issues, and the system is working good. And again, I want to thank, I put several companies up there. We were very fortunate. When we started this project, as you can imagine, churches have budgets, and it was right during COVID we were planning this project, and building material prices were just going crazy. So we were looking for any assistance we could, and I approached a number of companies, and they were very generous to us, extremely generous, either with donations or reduced pricing. So I want to recognize those companies that are up there. They helped the church make this project work and helped us put that system together. As of June, everything is up and running. Cooling is working good, and the winter's ahead, so hopefully we'll try to keep some more data. I don't have data loggers on the system at this point, but I've been pleased with how it's worked so far. And with that, I want to thank, first of all, the folks from HVAC for organizing the summit, bringing it out to Western Canada for the first time. And certainly I want to thank all of you for your readership in the articles that Robert does and the articles I do. And we all know the former contractor, Doug Picklick, that now is the editor that does such a good job editing our articles. And our website, if you're interested, we've got some information there, hydronicpros.com. With that, I'm going to thank you all and hand it back over to Doug.